To move 625 cubic meters of water every hour across nearly 18 kilometers of terrain requires serious infrastructure. This topographical profile maps that exact route. Pushing this volume of fluid up a continuous 200.5-meter elevation gain subjects the system to intense static pressure, requiring a strict 40 bar, or PN40, rating across the entire pipeline. Maintaining that steady-state flow is mathematically straightforward. The real engineering problem begins the moment that flow changes. Pump startups, power failures, or valve modulations can trigger transient hydraulic shock, a massive kinetic wave that violently slams through the steel pipeline interior. Absorbing and redirecting this surge of kinetic energy relies entirely on a highly specialized, mechanically sequenced network of valves operating autonomously along the route. In high-head transmission networks, we do not select valves based on flow efficiency. We select them based strictly on how they manage catastrophic system failure. The immediate isolation boundary between the pumps and the delivery header consists of 300 and 600 millimeter non-return valves. If a pump suddenly trips offline, the entire 200-meter vertical water column instantly loses its driving force and begins falling backward toward the station, threatening to spin the massive pump impellers in reverse at destructive speeds. A 90-degree swing check valve relies on fluid pressure and gravity to travel its full arc. Under high head, the reverse column accelerates so fast the 90-degree disc would slam into its seat with enough force to fracture the pipe casting. This split-screen diagram illustrates the mechanical solution. By shifting the seating angle to 50 degrees, the slanted disc design drastically shortens the travel path required to close the valve. Looking at the velocity curve added to the diagram, the shortened stroke allows the slanted disc to snap shut from gravity alone, long before the reverse fluid velocity can build to a destructive peak. Because the larger 600 millimeter header units still carry immense weight, external hydraulic dampeners and counterweights are bolted to the side to mechanically cushion the final 10% of travel. Eliminating flow resistance is secondary. In a 40-bar environment, check valve geometry must prioritize ultra-fast kinetic arrest to survive a pump trip. Further down the pipeline, situated at 4 to 5 kilometer intervals, are massive 600 millimeter mainline isolation valves cast from A216 heavy-duty steel. Standard concentric butterfly valves drag their rubber seals across the metallic seat during the opening arc. Under 40 bars of pressure, that sliding friction would rapidly shred the EPDM rubber. This wireframe cross-section shows how a double eccentric geometry solves the wear issue. The stainless steel shaft is pushed off the exact center of the pipe, labeled as offset 1, and also pushed slightly behind the center line of the disc, marked as offset 2. As the valve begins to open, these two offsets create a cam action. The magnified inset shows the rubber seal pulling away from the metallic seat instantly, eliminating sliding friction and ensuring a bubble-tight shutoff over thousands of cycles. Despite the minimal friction, the electric actuator turning that shaft is strictly geared to take 5 full minutes to complete its 90-degree rotation. Slamming a massive 600 millimeter steel disc shut against moving high-pressure water converts the flow's kinetic energy into an intense shockwave, triggering a devastating Joukowsky pressure spike that would rupture the line. Opening the valve against a one-sided pressure differential is equally dangerous. An 80 millimeter bypass valve must be opened first to equalize the pressure. Otherwise, the immense hydrodynamic torque could shear the main shaft completely. The mechanics of mainline isolation are highly constrained by physics, requiring a slow, carefully choreographed sequence to avoid catastrophic hydraulic feedback. Back inside the main pumping station, a pressure relief valve sits on the common delivery header. Working alongside the station's primary air vessel, this valve acts as a dedicated surge clipper. If internal line pressure exceeds the safe set point, it rapidly blasts open. This schematic details the pilot-operated diaphragm mechanism. Small hydraulic sensing tubes feed directly from the main line into a control chamber above the main valve, dictating its position without any digital sensors or PLCs. When the pilot tube registers severe overpressure, it instantly vents fluid from that upper chamber. The lack of downward pressure allows the immense line force to push the main diaphragm up, dumping excess water back to the jackwell. By relying purely on hydraulic and mechanical feedback, this overpressure protection remains fail-safe, guaranteed to function even during a total electrical blackout. Following the pipeline route over the changing terrain reveals 100mm triple-function kinetic air valves mounted on steel stubs at the high points and descending slopes. Their triple-function logic covers the entire operational spectrum, sucking in massive volumes of air when the pipe drains, venting large volumes out as the pipe fills, and slowly bleeding off tiny pockets of dissolved air while fully pressurized. Evacuating large amounts of air rapidly creates a serious aerodynamic problem. High-velocity exhausting air can catch a standard spherical float and slam it shut into the seal before the venting process is actually finished. This cross-section shows the vulnerability of the standard float on the left. The kinetic design on the right uses an aerodynamic Hostaflon or Teflon profile. This allows the high-velocity air to bypass the float without lifting it, preventing premature closure and eliminating trapped air pockets that would otherwise restrict water flow and cause unpredictable surging. While the main pipeline handles 40 bar, these air valves are often only rated for 16 bar. Because they sit at the highest topographical elevations, the static head they experience is drastically lower than the deep valleys. At the 16.1 kilometer mark, a particularly sharp, high-risk crest houses a specialized 150mm vacuum breaker valve. If a power failure causes the water column to physically tear apart at this crest, the resulting void generates an immense vacuum that will literally crush the 8mm thick steel pipe inward. As the internal pressure drops, external atmospheric pressure overcomes a heavy-duty calibrated spring inside the valve, throwing the massive orifice open to gulp in surrounding air and physically cushion the water columns when they crash back together. Large-scale steel networks are highly vulnerable to negative pressure. Engineering the ability to breathe air in is as critical as containing the high-pressure water inside. Dropping down into the physical low points, or valleys, of the pipeline, we find 200mm scour sluice valves used for deep drainage. These differ significantly from the smaller sluice valves beneath the air valves at the peaks. The difference comes down to localized seating materials. Gravity pulls sharp grit, sand, and heavy weld slag down to the lowest points, where the scour valves operate. Closing a rubber seal over that sharp debris would tear it to pieces. To survive, scour valves require heavy-duty bronze metal-to-metal seating, capable of crushing through the grit. Conversely, the isolation valves at the top of the pipe handle only clean water. This clean environment allows engineers to use softer EPDM rubber seats that provide a perfect zero-leakage shutoff. Both variations utilize a non-rising spindle design. Because they are installed inside compact underground concrete chambers, turning the handwheel pulls the wedge up an internal threaded net, keeping the stem from crashing into the chamber ceiling. Every internal seating material and mechanical geometry is matched precisely to the localized microenvironment the valve occupies within the larger network. To see how this entire architecture performs collectively, we must stress test the system with a total electrical blackout at the pumping station. This system-wide schematic maps the event. At T0, power drops. The massive pump motors trip offline. By second 1, the 625 cubic meters of forward flow lose momentum and the vertical column begins to fall backward. At second 2, gravity and hydraulic pressure force the slanted disc non-return valves to snap shut, catching the falling column and sealing the pumps off from the main line. By second 3, the sudden halt of thousands of tons of water creates a massive vacuum wave that races up the pipe and strikes the 16.1 kilometer crest. Between seconds 3 and 4, the vacuum breaker valve springs open to pull in atmospheric air and prevent pipe collapse. Simultaneously, back at the station, the compressed air vessel discharges its pressurized water payload into the header to prevent the column from separating. At second 10, the kinetic wave rebounds off the vacuum cushion and returns to the station as a high-pressure spike. The surge hits the header, forcing the pressure relief valve to blast open and dump the excess kinetic energy into the jackwell. Over the next 5 minutes, the system slowly calms. The network of kinetic air valves quietly bleeds out the ingested air, restoring stability to the line without a single digital command ever being executed. The ultimate survival of a high-pressure water transmission network relies entirely on the passive, hard-engineered physics embedded in its valve architecture.